In this video, I introduce a beta variational autoencoder, learning basic visual concepts. Variational autoencoders learn latent representations of image data in unsupervised manner. Beta VAE is an improved version of VAE by introducing a adjustable parameter beta to balance latent channel capacity and independence constraints with reconstruction accuracy. Beta VAE learns disentangled representations, for example, skin color, age, gender, or image saturation, as shown here, of independent visual data generative factors in unsupervised manner. A training dataset D consists of images X and two sets of ground truth generative factors, namely conditional independent factors V and conditional dependent factors W. The goal is to generate the image X condition on V and W. Beta VAE uses the samples from X to learn the joint distribution of data X and a set of generative learned factors Z, so that Z can generate the observed data X. The objective is to maximize the marginal log likelihood of the observed data X in expectation over the whole distribution of latent vectors Z, as shown here and here. For a given observation X, the posterior Q phi of the latent vectors Z captures the generative vectors V in a disentangled manner. The conditional dependent data generative vectors W can remain entangled in a separate subset of Z. Q phi is forced to match the prior P, for example, Gaussian distribution, to capture the disentangled property in the input image. The constraint optimization problem is defined as here, subject to D KL smaller than E, where E controls the constraint strings. The constraint optimization problem can be written as a Lagrangian, as shown here, where the Lagrangian multiplier beta is the regularization coefficient that constrains the capacity of the latent information channel Z and put implicitly independent pressure on the latent posterior due to the isotropic nature of the Gaussian prior P. Since beta and E equal or larger than zero, the beta VAE formulation can be written as here. Variant beta changes the degree of applied learning pressure during training, thus encouraging different learned representations as shown here. This constraint beta larger than 1 is used to enhance the constraint. This constraint P is used to generate the output. To learn disentangled representations of V, beta is set to be larger than 1 to strengthen constraint on the latent bottleneck than in the original VAE formulation. The constraints with the beta larger than 1 limit the capacity of Z, which encourages the model to learn the most efficient representation of the training data X. Since the data X is generated using at least some conditional independent ground truth factors V and the D KL term in the beta VAE objective function encourages the conditional independence in Q phi. The high values of beta encourage the learning the disentangled representation of V. The disentangled representations are reached at the right balance between information preservation and latent channel capacity restriction. Since beta directly affects the degree of learned disentanglement, it's better to estimate optimal beta for the learning disentangled latent representation directly. However, it's impossible because the optimal beta depends on the model architecture, the training dataset, and the E values. Here, the human had disentangled factors in latent space. Disentangling metric measures independence and interpretability of the inferred latents, namely conditional independent data generative factors correspond to some property of the generated data. A simple linear classifier is used to ensure no capacity to perform nonlinear disentangling. The accuracy value is defined as a disentanglement metric score. Assuming the label Y, as shown here, can identify a subset of independent data generative factors V, for example, scale, position, and rotation. Each batch consists of L pairs of examples, as shown here, with one fixed generative factor and randomly sampling others, as shown here and here. A batch of B vectors ZB is constructed and then fed into a linear classifier following the steps below. This is a linear classifier. First, choose Y from a list of factors as shown here, where key is the number of factors. Second, for a batch of L examples as shown here. A, compute Z1 and Z2, for example, here, by using this encoder. And enforce Z1 is equal to Z2 if K is equal to Y. B, reconstruct X1 from a simulator, then enforce Z1 by using this encoder Q. Repeat the process for Z2, as shown here. The difference ZL is the absolute linear difference between the inferred latent representations. 3. The linear classifier uses ZB to predict a P, and the accuracy value is defined as a disentanglement metric score, as shown here. A linear classifier predicts the index Y given ZB to generate the factor Z1 that corresponds to the specified property of the input data. The difference ZL of two inferred latent vectors Z1 and Z2 is used to reduce the variance in the inputs to the classifier, and to reduce the conditional dependence on the input X, which ensures on average ZBY smaller than ZB exclude Y. For more details, please check with these references. Thank you.